Maybe to get us going, we can start to introduce ourselves, so you know who will be talking to you. Maybe Sarah, do you want to go ahead and say who you are and what you've been working on as part of the COVID response of the national labs?
Sure. Hello, everyone. I'm Sarah Del Valle. I'm a scientist at Los Alamos National Lab, and I've been part of the modeling response. My background is in applied mathematics and computational sciences, so I work a lot on developing epidemiological models for the spread of COVID-19.
Great, thank you. Michelle, do you want to say, you've played lots of roles in this.
Well, I'm Michelle Buchanan. Up until recently, I was at Oak Ridge National Laboratory, and now I'm on special assignment as a senior technical advisor to the Deputy Director for Science Programs at DOE. And I played a role in NVBL as the one of the two original co-chairs of NVBL.
Thank you, that's great. My name's Kirsten Cleese van Dam. I'm from Brookhaven National Lab, computer scientist, and we have put a great program together at the lab, together with many other labs, actually. That's one of the hallmarks of this program, that we collaborated across the 17 national labs to pull all the resources together. To put a number of exciting projects together to help the nation. In our case, we were very much focused on discovery of new treatments for the COVID virus, but many other things as well. And we'll have the opportunity to talk about that. Maybe for those that don't know so much about the national labs, so the Department of Energy has actually 17 national labs with slightly different focus areas, and we are spread across the whole country, usually in friendly competition with each other for what we want to do and to excel at the science that we are doing. But when it comes to big events like this, where the nation is in crisis, we're all coming together to build large teams to tackle those challenges. And this is exactly one of those challenges where we've done that. I think what we can do is maybe start with some of the first questions, so we can tell you a little bit more about what we've done. Michelle, complex problems like solving COVID-19 require a multi-layered response. Epidemiologists working with mathematicians to model disease spread, structural biologists working with virologists to understand the role of the proteins on the virus, and chemists working with computer scientists to help predict which candidate molecules might be able to neutralize the virus. Tell me about why the National Lab System is ideally suited to solve these kinds of interdisciplinary challenges.
Thank you, Kirsten. The DOE National Laboratories are truly incredible resources in the nation's science and technology enterprise. Across the 17 laboratories, literally tens of thousands of scientists and engineers come to work every day, representing a wide array of expertise, and they all focus on DOE's mission of developing new clean energy technologies, protecting the environment, and ensuring national security and the economic growth of the nation. The breadth of this expertise, is truly incredible, and that's one of the reasons why the labs are called upon by the nation when emergencies like COVID come up. But further, unlike universities and other laboratories, our staff can quickly pivot to form multidisciplinary teams so they can respond to these emergencies basically in real time. But in addition to the expertise that the laboratories have, they also have incredible resources to conduct this research. And this includes the 28 user facilities, such as the light sources, neutron sources, computational facilities, and even the nanoscience centers that can support not only the research community within the laboratory, but the broader research community in the nation. So with this broad area of expertise and the type of capabilities, the national labs have the ability to respond very quickly. And this is what the labs have done since they were formed back during the Manhattan projects in the 1940s. And in the case of COVID, we've seen just in the last year that when the call came up to work on the COVID project, the 17 national laboratories responded, and over 700 lab staff joined forces and formed into 5 teams to combat some of the most important aspects of the COVID crisis.
That's right. Thank you, Michelle. Basically, collaboration is built into our DNA. Sarah, maybe you can talk a little bit about COVID is obviously the crisis that's currently on our mind, but this is not the first time that the labs got together. Maybe you can talk about some of those challenges that you have been involved in.
Yes, so the national labs, and not just myself and and Lano, but across the labs, we have responded to many different disasters. For example, we always respond to hurricanes. Well, Hurricane Katrina, Hurricane Sandy. We have provided impacts of the electric power outages, which we've seen recently also in Texas. We also help with analyzing the cascading impacts of those outages on other critical infrastructure such as water, food, healthcare. And we also help with modeling evacuation in those kinds of situations. So hurricanes is one of the things that we always support. Also, COVID-19 is not the first pandemic or epidemic that we have supported. The national labs were involved in the response of the H1N1 pandemic influenza. And in fact, I was at the White House a few times briefing science advisors, and we provided a lot of products that provided decision support in terms of the potential impacts of population, economic, and healthcare impacts of the H1N1 pandemic. We've also helped with the Ebola outbreak in West Africa on developing vaccine designs, rapid diagnostics, and also epidemiological modeling of the spread and the impact of different mitigation strategies. And additionally, when the chikungunya and Zika pandemic outbreaks appeared in South America, we also helped in the response of those epidemics. And additionally, the labs have built significant capabilities to help with wildfires. And so we are able to understand the dynamics of the fires and help first responders understand the severity, the path, and the intensity of those fires so that they can hopefully mitigate their impact. And so those are just a few of some of the natural disasters that we've helped, but we have supported both natural and man-made disasters.
Yeah, it's a really great way of working. I joined DOE in 2009, and then shortly after we had in 2010 the oil spill in the Gulf, and after that Fukushima. And I was just amazed at how quickly scientists came together to address these kind of challenges, and the whole lab system got together, looked at how can they help, how can they bring their expertise to the table. That was just fantastic, something I haven't seen in other countries.
Can I weigh in?
Yes, please. I was just about to say we're very pleased to have you here.
It's so funny. You were doing a great job. I was watching the whole thing. We were having just a little bit of a technical issue on Zoom for whatever reason. And Tanya, who has been organizing this, I know I saw her flick on and off, and I just want to say thanks, Tanya, for that. Yesterday was her birthday too. You guys have been doing a great job of getting us started, and thank you for that. Kirsten, you're an amazing moderator, and if this thing as a scientist doesn't work out, there's another job in there for you. So So let me just pick up where you all left off. Obviously, this is intended to give people who don't know about the labs, which you started to explain about, some idea about the amazing work that you all are doing. And I don't know, I mean, the 17 labs that you talk about it all the time, but real people out there, I like to think of like my mom or my Aunt Linda, who are just not following this, may not realize when we say 17 national labs, we're not talking about 17, labs with 2 people at a bench. We're talking about 70,000 people in America who are spread across America solving problems. And the DOE is the solutions department, and you see some of the greatest problem solvers on your screen. So it's super exciting to be able to talk about this particular issue, which is the issue of the day, clearly, the COVID vaccine, and what the labs have actually been doing about it. So because Michelle, you were the co-founder of the virtual lab, which connected all of these labs together, I'm wondering if you can just go a little bit further than what you already did, which is, beyond understanding the biology and the epidemiology of the virus. The labs also, they tackled the supply shortages, right? On everything from masks to ventilators. And I think, if I'm not mistaken, you did that by bringing teams together, I guess virtually, right? To design and to manufacture prototypes that could be scaled up rapidly. A lot of people don't know that. So I'm wondering, as you think both back, but also forward, what are some of the lessons that we have learned so the next time we are, if we're confronted with a crisis like this again, and there will be other pandemics, that we have all these pieces ready to go so we can get out of the gate running. What are those lessons?
Well, I think you hit it on the head. I mean, bringing the people together rapidly, and some of these people were thousands of miles apart. Some of them hadn't even worked with each other before, and to have people just put all of their effort, just really a sense of urgency to get these issues addressed was really remarkable. But I think that another thing that really helped the National Lab System is they don't work in a vacuum. So they have a lot of contacts with universities, with private industry, and with other federal agencies. And that really helps, because in a situation like this, you want to be able to respond and come up with the right answer that will be useful and that can be taken into the private sector and put to use right away. So one of the things the laboratories did is rely on the relationship they have with industry, because they do work a lot in taking any energy technology and other things invented within the laboratories and spinning them out to the private sector. So the NVBL manufacturing team is a good example of that. And here is a team that had deep expertise in materials science that's been supported by basic energy sciences, and at advanced manufacturing that has been supported by EERE, and brought all that to bear.
All right, wait. All right, can I just say, if my mother's listening, you're using too many acronyms.
Okay.
You said NVBL, just for everybody knows, National Virtual Biotechnology Lab, EERE, right?
Yes. Energy efficiency and renewable
energy, which is a big part of the department. Go ahead.
But
the no acronym zone.
Okay, we're gonna keep away from acronyms. But I think it was important because a lot of the people who worked on these teams had contacts in industry that they could go to as resources as they were working on the COVID problem. And example is there's a carbon fiber facility in Oak Ridge that is set up to look at research in developing low-cost carbon fiber. This was converted very quickly over to making the non-woven fabric that they use in the N95 mask. Now, in addition to making the fabric, you have to put a charge on that fabric, because that's what helps keep the virus from permeating through the fabric material, okay?
What do you mean put a charge for people?
A charge is an ionic charge. So you put a positive charge or a negative charge, and basically it attracts the virus, okay, and keeps it from going through the mask. And this is an important aspect of making these masks. And it so happens that one of the people working on this project had a next door neighbor that he realized was the original inventor of the N95 material 25, 30 years ago. And so that individual came and worked and helped develop the process for reproducing the N95 material. once they got that done, they had to verify that it was really an effective media. And so they used the X-ray sources at the national labs as well as the nanoscience centers, and they were able to verify that it met FDA qualifications. So what next? They reached out, and this is kind of an incredible coincidence. They reached out to Cummins Diesel Company, of all places. And Cummins, they work a lot with the laboratories to develop efficient diesel engines, but Cummins also makes filter media for air filters. So they reached out to Cummins and said, you know, how about looking at this and seeing if you could convert one of your production facilities to make the N95 material. Cummins was very interested, and now they have lines at all 5 of their air filter facilities making N95 filter media. And then they went a step further, and the team reached out to Dematec in Florida and helped them set up lines to make the masks themselves out of the N95 materials. So in very short order, this team working with industry got this technology out, and masks are being made now by the millions. And the other thing that was really remarkable is not only did they get masks on the floor, but they also created over 1,500 new jobs. And so this was a very successful project that came out of the NVBL.
Well, I mean, so interesting because these labs, there are 17 of them, and every one of them have hundreds of contacts, both in the private sector and in the community. You were able to really bring that together, which is really what a network is all about. So very cool. Let me just jump to the virus itself and what people are doing. Kirsten, I mean, one of the many important accomplishments of the National Virtual Biotechnology Lab was the work of DOE scientists to decipher, I think, the critical parts of the virus. I mean, I think you were taking actual high resolution pictures of it to see, like, really blown ups, to see what it looked like so that drugs then could be designed to counter it. And I wonder if you can walk us through that process and how it works.
Yeah, absolutely. So what you have to understand first is that the virus is very small to start with. So it's the whole virus is about 50 to 140 nanometers. And the spikes that most of you will have heard about, these little blobs that are standing out there, sort of 9 to 12 nanometers. Now, if you're like me, you can't imagine what a nanometer is. Well, if you think of a piece of paper, that's the thickness of a piece of paper is 100,000 nanometers. So that's
amazing. That's
small,
amazing.
how small this is. And we don't just want to take a picture of it sort of afar, but we really want to go into the nooks and crannies of it to see where there are possible weak points, where we could attack the virus and prohibit it from spreading, from latching onto the human body, or containing it where it is. So we really had to have high resolution pictures or imaging of it. And we didn't just want to know the structure, but we also wanted to see how it functions, how it behaves, and then also how it interacts with different treatment options that are out there. And those are really the 3 key things. And to be able to do that, we needed to prepare samples that could be safely examined. And then Michelle already mentioned, we have this great resource in our light sources. We have 3 in the US that are operated by the DOE. And it's their bread and butter to do these kind of things. Look very specifically at things that are very small, trying to figure out how they work. And so they were one of the few, and I really admire my colleagues for that. They were the ones that were actually on site, having to work out how they can do this safely during COVID. And we, for example, at Brookhaven, we even built a new facility which gives further capabilities to look at the virus during the pandemic, getting it ready as quickly as possible so that we could help in the effort. And so we did this, and the way it works is initially you get the structure, so what it looks like, the virus, and then you would use technologies that we've developed using artificial intelligence and high performance computing to look at what potential treatments there could be to attack the virus, Once we had down selected those into a few options, they would then be made again, and they go back to the light source to see, well, do they behave as we had predicted it? And then we can take it further. Yeah. So there's a whole cycle of work. And I have to say that the light sources have done a tremendous job, not just for the NVBL, for the Natural Virtual Biolaboratory, but they have actually been supporting industry. So all three light sources have worked throughout with the pharma industry, looking at their different options, helping them to refine and to improve their medications. And they've been, for example, involved in the development of all the vaccines that we know today.
Okay, I was going to ask you that because you talked about therapies, but it's also vaccines as
well.
It's
also vaccines,
it's
yes.
For all of that. So are you continuing to look at the new variants that we keep hearing about to see what, how they're changing and whether they might require some new therapies or a different form of vaccine?
Yeah, absolutely. As we all know, there's new variants coming out, and some of them are, it's just like your T-shirt changing color. It's just a different color, and it doesn't matter. But others have really critical impact. We've all heard about the UK variant or the South African or the Brazilian, which appear to be much more effective, and so that clearly has an impact, and we have to look at it. How they respond to treatments and to vaccines.
Yeah.
What we do is we work actually quite closely with the NIH and tracking the new variants, looking at the different families and looking at where the changes are. And if those changes are talked about, the weak points that we are attacking with treatments and vaccines. And when a new variant flags up as being impactful and in the area where maybe currently the vaccine or the treatment is working, then we look at it in much more detail and follow up, basically. Again, we use then our initially high performance computing and modeling to see how the virus has changed and how its behavior might be changing because of the structural changes. If we then find that it really inhibits the working of a vaccine, then we go back to the cycle using our artificial intelligence infrastructure and high performance computing to look for different treatments that could be done.
Mind-blowing.
And obviously we also have to look at, so we had a different group at the labs working at the testing regimes that you need. And so they would, again, that would be something that would be triggered if the virus has changed quite a bit.
It's amazing, and especially given the various specializations of the labs and, artificial intelligence and the high performance computing, as well as what is already being done, whether it's in critical materials or in photo, in imaging, and so much happening. So let me flip over to the policy side for just a moment, because of course the American Rescue Plan, the package that is being considered by Congress right now, and the future of the pandemic will depend upon what people like me, formerly politicians, do. So Sarah, let me ask you this, the American Rescue Plan includes funding for a vaccine rollout. And I want you, if you can, to talk to me about the types of vaccines, the 3 types that we know of now, right, that are currently available, and how the American Rescue Plan is going to impact vaccine distribution.
Yeah, so as you mentioned, there's 3 vaccines, the Pfizer, the Moderna, and Johnson & Johnson. Let me just give you a little bit of information about these vaccines. So the Pfizer and the Moderna require 2 doses and use the messenger RNA technology, which is a new technology to develop vaccines. The Johnson & Johnson vaccine requires only 1 shot and use the traditional virus vector approach that has been used for many years to develop other vaccines. And so although there are differences in doses, technology, efficacy, and storage requirements, which you probably hear about, the evidence suggests that all 3 vaccines are effective in preventing serious and life-threatening disease. And so we recommend all 3 vaccines for those people who are eligible to get the vaccines. So now, in terms of how the rescue plan will help, by having multiple vaccines, obviously we're going to be able to have more availability and more Americans can get the vaccine faster. The Johnson & Johnson vaccine only requires 1 dose, and so that will probably help administer and distribute more vaccines quickly. However, you know, Kristen mentioned, and you mentioned the new variants, and so we need to recognize that, as she mentioned, the variants are naturally occurring. So it's, you know, viruses mutate all the time, but we are concerned with the South African variant because the vaccines appear not to be very effective against that variant. And therefore, the sooner we can get everyone vaccinated, the sooner we're going to be able to mitigate the potential impact of that variant on the population. And so we are trying to hopefully get herd immunity through the vaccines and through the American Rescue Plan. I think that will probably facilitate.
So, but on that South American, since the vaccines appear not to be so effective against it, will herd immunity help to make sure that at least it's slowed? I don't understand how that works.
So the vaccines, even though they're not, you know, you've heard probably the 95% effectiveness for Pfizer and Moderna, or 85, 86 for Johnson & Johnson. For the South African variant, it seems like they're, you know, less than 50%, 46%. So even in our models have shown that even with a limited protection, even if it's 40% or 50% protection, you're still able to mitigate the spread because now you have less susceptible population that the virus can, you know, attack. In that even that limited effectiveness can actually make a huge difference, and especially obviously in combination with face masks and social distancing and all these other non-pharmaceutical interventions. I think the combination of those interventions and actually help break the transmission of the
and
virus.
Then, I mean, like the flu, right? Everybody gets a flu shot every year. One would imagine that the next version of vaccine rollouts would include, I mean, they're going to be testing and trying to find a vaccine variant that is effective against that particular South American variant and any others. So I imagine, one could imagine that this vaccination issue is something that we're going to have to perfect, I will say, over the course of time. Is that fair to say?
Oh yeah, absolutely. And as you know, there are many new vaccines that are being developed that are targeting those specific variants. And in terms of the lab's role in the vaccine design, we are helping design vaccines, and also Kirsten's lab is also helping with that. We are also helping with using epidemiological models to assess different vaccination strategies. We have been working closely with the CDC, the WHO Immunization Working Group, the White House COVID Task Force on assessing different intervention strategies. So we know we have a plan on how to vaccinate, but we're also assessing what happens if we vaccinate vulnerable populations that we know have been disproportionately impacted by COVID. And so we are trying to compare those scenarios versus the scenarios that we currently have to see how that could potentially help in mitigate the further spread and the impact of COVID on those communities.
Great. Well, something tells me this is not going away. Just a couple more questions quickly. Kirsten, obviously everybody's worried about schools, right? And the American Rescue Plan includes funding to schools so they can better implement protections, like improving ventilation, for example. Can you talk just briefly about the way the virus spreads through the air and why that particular funding is important to keep children and teachers safe as we hopefully transition back fully to in-person activities?
Yeah, that would be great. Yes, so we've done quite a bit of studies. As most of you will have heard, if you are infected and you're breathing out then basically the virus becomes airborne. And what we call this is it creates, we create aerosols, which are sort of particles that float in the air. Now, aerosols is nothing sinister. They're all around us. If you think of fog, of mist, of dust, smoke or pollution, all of those are transported by aerosols. So as a national lab, we actually know quite a bit about that, because we study pollution and smoke and things like that. So with a virus, we addressed this in the same way, and we looked at how do those aerosols move, basically those virus-laden aerosols through the air. What we learned from the medical side is that it depends to infect someone else. So if you think of a space, there's two people, one is vulnerable, one is infected. It depends on the amount of virus that arrives at the vulnerable person and how much they breathe in. So when we look at this, we then think about different spaces and how the air moves through them. Obviously, if you have a completely small and confined space, then what I breathe out will be all around you, and you get a full load of it. However, if we were outside and there's a lot of air movement, the air that I'm breathing out is mixed with clean and healthy air, then this disperses, and the load of the virus particles that arrive with you are much smaller. And so using that knowledge, we then did quite a number of studies. So first of all, we looked at, well, if we have a mask on, different mask types, how much virus load comes out when I'm breathing? And obviously we could see very clearly the reduction in virus load if you're wearing a mask, even if it's not tightly fitted, but even that already helps. The better the mask, obviously, the more it helps. What we then further looked at, and that comes back to the schools, and we said, okay, I have school children, you can be sure they're not all wearing their masks all the time, even if they're maybe supposed to, and the mask will be moving or they won't wear one. So how does it work if they're on a school bus, if they're in a classroom setting, if they're in a courtyard out dining, makeshift structures, all those kind of things. So we look through all those different options, and when I'm saying we, I mean people at many different labs that we have did those kind of computer simulations, but then also practical tests. Some of our offices at DOE were supporting us as well in this to do the experiments, and then we could get a picture of how we can reduce the virus load in the air. And obviously ventilation is a big factor in that, but it's informed as where you would bring the ventilation in and where it can make the most difference. And I think Michelle can talk a little bit about the building technology offices that were helping with this as well.
So bottom line is, though, just how do you communicate what the best practices are to schools all across the country? How do they know what to set up and what to do?
Yeah, and that's that. So we've worked with some school districts directly, but I think there could be a lot more done to get those messages out, because it really depends on the space that you are in,
right,
and also on the HVAC systems that you have, what they're allowed to do. Obviously, the national labs themselves are little laboratories of their own. We have different
literally, yes.
buildings. Yes, exactly. We have different types of buildings, and so we came up with different measures based on the type of building and the type of building infrastructure that we have, and we would be very happy to share those experiences, look at new spaces.
That's going to be critical. We're going to continue to focus on that, getting the word out, obviously, in all things, the great work that the labs are doing, but putting them into the hands of those who can make best use of it. I mean, Michelle, you know, you're the virtual lab, the virtual biotechnology lab, set up in order to collaborate. Can you imagine that this model is going to be used to help solve challenges beyond COVID?
Oh, I definitely think that that's going to be the case. I mean, the fight against COVID is still going, and it's still things, as we talked about, is something we need to continue to keep battling with the expertise and capabilities of the national laboratories. But if you just look at the construct of NVBL, it was a very unique construct when it was set up. It included having kind of a central focal point, which was the executive committee, which was comprised of people from headquarters and people out in the field like Stephen Stryford and Marianne Walk and myself representing the national laboratories. And this central group then reached out to single points of contact at each of the 17 national laboratories. These were typically the chief research officers, and they were able to reach back into their laboratories to find the right people to put on these teams. And so the 5 teams were identified and stood up and got to work very, very quickly on this. So that communication to the laboratory, having a single point of contact communication plan was very important to reach down into the laboratories. But just as important, maybe more important, was having that single point of contact to reach back out of the laboratories. And so the executive committee had contacts with the FDA, with CDC, with NIH. And instead of having all these agencies reaching out to single laboratories and trying to find the expertise that they needed, having that single point of contact really helped. And I think actually the amazing thing was that I think it taught these other agencies the incredible resource that we have within the national laboratories that they can make use of. And I think that's something that should go forward in the future. But you know, I think this framework is something that needs to be emulated in the future. And I'll have to tell you, I've been in the national labs for 40 years, and I have never seen an instance, sorry, I'm old.
You look good though.
But I've never seen an instance where I've seen so many people come together with such a sense of urgency to attack a problem. It was simply amazing. And I think the construct works very well.
It's an inspiration. We at DOE tells you we're not going to take any of this stuff sitting down. We are going to use every tool in our arsenal. And of course, the tools of the labs are massive. I want to thank you so much. I mean, Kirsten, particularly you for kicking us off in an unceremonious beginning, but still it worked out totally fine. So Dr. Kirsten Van Dam, thank you so much. Dr. Michelle Buchanan, excuse me, thank you so much. Sarah Del Valle, thank you so much on behalf of not just me, obviously. And by the way, I didn't even introduce myself. My name's Jennifer Granholm. I'm the new Secretary of Energy, but on behalf of really 330 million Americans who may not even know about the lab system, certainly don't know about any of us, but who are counting on us to solve the biggest problems facing the country. So I'm so proud to be part of this. And I just have to note that it is Women's History Month, and we have all these great women leaders, great women scientists on deck, which is phenomenal. So thank you all very much for joining us. We're going to do these as a series. We'll get our technology down, you know, as in science experiments, you try and try, you learn what you didn't do right, and you pick it back up. So thank you everybody so much. And a particular shout out to Tanya Das, who arranged to make this happen. Stay tuned, everybody. This is not the last you'll be hearing from us. Thanks so much.
Thank you.
Thank you.